November 21st. Okay. So in November 21st, the second workshop, innovative lecture, as it's called in different way. Okay. So will be on adaptive filtering. And so for this reason, I prefer to discuss together about adaptive filtering in advance, which means now, so that you have time a little bit to reflect, to think about, okay, and perhaps you come to the November 21st workshop time more strong and ready to work on the data. Now, I don't have the slides, so I'm using the book. The reason why is because I choose to swap, to make the adaptive filtering today. I decided 20 minutes ago, okay, when I knew that we have a room. Okay, so we have a room on Wednesday. Now, so what is adaptive filtering? So what is adaptive filtering? Adaptive filtering has to do with the possibility to change the filter according to the context, according to the environment. Now, you can change the filter, you can change the estimator. So the estimator is changing according to the signals that we are manipulating. Now, since we haven't been doing the Bayesian estimation, okay, so when we do the Bayesian estimation, we will see that if the processes are stationary, then we can design the optimal filtering. But if the processes are not stationary, so if we have a random process, the random process is non-stationary, then we have no theory which is supporting us. In other words, I have no theory which is telling to me what to do and how to make the filter if the environment is non-stationary. Okay? Now, it's, what kind of non-stationarity we might have. So if this non-stationarity is not very quickly varying, then we can figure out that we can adapt our estimator in such a way that the estimator is changing smoothly versus time. Now, all that has to do with that is called adaptive filtering and adaptive estimator. Now, rather than starting with a lot of words, let me start with an example. Okay. Now, the example is the adaptive interference cancellation, which is the active headset where you have a system where you cancel the noise, outside noise, so that you reproduce a very clean signal. Now, let me look at that. So this is the system. Okay, I'm starting, as you see, I'm starting to motivate you, okay, by an example. So this is an active headset with active noise cancelling. Okay, this is the word. Technical word is active noise cancelling. But don't be stick on the word. Let's reason a little bit on what is the concept. The concept is the following. If I have my headset is reproducing the signal, the music that comes from our equipment, and at the same time, I have some external noise. So the external noise is damaging the signal. So it's, imagine I put my headset in an helicopter. Okay, it's very noisy. Just to say, a very highly noisy environment. Okay. Now, how can I just cancel this noise that comes into the headset? The way is the following. So imagine that my device is measuring the noise. So if my device is measuring the noise, then I can send to the headset a signal that contains the noise with the opposite sign. So that I have a positive noise which is coming from outside, and the negative noise which is reproduced from here, it goes into the headset. Okay? Now, in this way, this cancellation of the noise reproduce a clean signal. Okay? Now, so now where this device, which is the active noise canceller, is positioned, it doesn't matter. So I can put into the headset, I can put into the external device, I can put the microphone on the top of my headset such that this microphone measures specifically the noise. I was at a meeting in Rome, and there are some hearing device which contains a noise measurement, and so they actively cancel the external noise, which is very annoying for deaf, okay, for the people that cannot listen. Okay, so that's the system. By the way, this has a glass which is similar to mine. So that's just to joke a little bit. So now, how does it work? So because we need to say how this system works. Now, it works very simple. Okay, in principle, it works very simple. So this, everything that goes into this box is representing the system. Okay, but everything goes to this block is something that we cannot open it. Okay, because it's the acquisition system, is the system that is reproducing the music. Now, SN is the music. Okay, and what I get is the following: that I want to make a very complex processing such that this signal, okay, is affected by the interference. And so when I listen to music without this device, I am listening here. Now, actually, this is the signal, which is the music. This is some noise which is coming from wherever. And then there is the interference. So this is the signal plus noise plus the interference that I measure at the headset without the noise cancellation. Okay? Now, what I do is the following. I measure X. Now, X is not exactly the interference. It is proportional to the interference, with respect to a time-varying filter. Now, why this filter is time-varying? You need to imagine that, the external noise is somewhere here. You can imagine it's helicopter, pop, 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 okay? And then, what is annoying me is that the external noise goes in. So it's not important the absolute noise of the helicopter. It's important the noise that the helicopter enters into my ear. Okay? So what I make a measurement XN, which is correlated to the helicopter noise. Now this XN, is not necessarily exactly equal to the interference that goes into the headset. Just to make an example, imagine that this measurement of XN is placed by a microphone here, and this microphone gets XN. Okay, so since XN, the microphone goes there, the interference coming from the external noise source is not exactly equal to the interference IN. But there is a filtering in the middle, which is due to the fact that, when I'm in a helicopter, or I listen to music, or I talk by the phone, because there is an active noise cancelling in the phone as well. So I move my head, okay? So when I listen to music, so I move my head in some way. This means that if there is a source of noise, wherever it is, okay, since I move my head, the filtering factor, which is correlating this IN and this XN, is time varying. So this filter is indicated by this X here. And this is what I measure. So now this is the black box. So the black box means, everything that I cannot really access directly. So what I can do? I can do the following. I can take this noise only, which I measure, I don't know, from another microphone. Now this other microphone is only measuring the interference, is only measuring the noise. Now this microphone in a helicopter can be placed around the helicopter, so in the cabin, in the cockpit, such that is measuring this noise. Okay. Then I take this noise and I'm filtering this noise. Now I filter this noise such that I estimate the theta hat. This estimate of theta hat is estimating the noise, because this cannot estimate the signal. So Sn is the music, just to make it more pragmatic, okay? Here is the music, and here there is the interference. And so, if I have an interference and I filter interference, I get the interference. I don't get the music, okay? So, it's impossible that I take the interference and, the output is the music, exactly the music that I want. Because, it's only because it's totally stupid, but it's because if you look at the two random process, the random process representing the music and the random process representing the interference, these two are statistical independent, right? Because they have nothing to do. Noise is something, and the music is another, okay? So, so for this reason, when I take the interference, the measure interference, and I filter that, since I try to estimate the signal plus noise, but since, there is no music component into X, by filtering, I only estimate the noise, not the music. So when I remove this estimate of the music plus noise from the noise only, filter noise only, what comes out is only the music. And so now, in this way, the signal that I get here is a very clean music signal, plus some noise. Now, what is this WN? You see, this WN is not correlated with the interference. I cannot cancel that. So I can predict, I can cancel everything which is in some way correlated with the statistical property of the signal that I want to remove. Okay? So now, how to make it? Now, the way to make it is the following. Because I have seen from the intermediate sum that what is a filter, okay? You understood that. Good. So, that the filtering AZ in Z transform is characterized by a set of coefficients. So, this A bold is a set of coefficients that represent the filter response, okay? So, just to exemplify, if I consider this, okay, and this AZ depends on the set of coefficient A, which is A0 plus A1Z to the minus 1 plus A2Z to the minus 2 plus blah, blah, blah. Okay? Plus A and Z to the minus N. Okay? So that means that I have this one, okay? All that contribute to the vector A. Okay? So the vector A is establishing what is the impulse response of a filter such that this impulse response is removing the interference. Okay? So, now this A is my unknown. So how can I make it? Now, first of all, in this system, my filter should be changed. Now, this, when I say time varying, is indicated by this arrow. So this arrow indicates that the filter is time varying, just as a mnemonic that the filter is time varying. So I have the system H, which is representing my movement of the reference and measurement with respect to the true interference. And so since this one is time varying, this one has to be time varying as well. Okay? So just to make it very simple, if this HZ is a filter with zeros, This AZ is a filter with the poles, right? Okay? No. So if this one is a filter with a couple of zeros, this one is a filter with a couple of poles. If this one is a filter with two zeros, one inside and one outside of the circle, intermediate exam, this one is a filter with two poles. And the two poles should be both inside in order to invert exam. Okay? So anyway, so this is the filtering that I'm implementing. Okay? Now, but if since the filter is changing, this AZ is changing. Okay? So it's now how do I change it? Now the way to change it is because I'm taking the signal here and I'm learning how to correct the filtering coefficient, trying to minimize what? Minimize this error or the error square. Okay? So everything is based on the minimization of the mean square error because I calculate the square error, but then I make the mean for that. Okay, intuitively? Now, so let's write an equation. Okay, so write an equation, but you know it's very simple. Write an equation. The problem can be framed the following way. Let me put both. This and that. Okay. Now, what I'm doing here, I'm writing in formula what I say by word. Now, what is the error? Now, the error is theta minus theta hat. What is theta hat? Theta hat is simply taking x and filtering by filter response A. Okay? So, write it. So, epsilon is equal to theta minus theta hat. Now, theta hat depends on the filter coefficient, which is indicated by A. And so, you know, by describing, which is simply that, by describing that, I know that the filter coefficient is obtained by taking the set of coefficient of A, multiplying, so the inner product with the set of xn. Okay? So, in other words, means that I have my, you know, my signal here. Okay, this is xn, and I'm taking a block of data, take this block, multiply by A transpose, and then, you know, I get the theta hat. Okay, so this is simply that. So this one is the filtering. So what is the mean square error? Now let's write it. So it's the error square mean, taking the expectation. So when I take the expectation, you know, I need to take the expectation with respect to the two random terms. These random terms are processed. So when I take the expectation about that, I need to take the expectation with respect to theta, and I need to take the expectation with respect to x, because x is random. Never lose the control of what you are computing. Never. Okay. So now, that means that what I need to do, I define this metric, and then I need to calculate the mean square error, and I minimize the mean square error. So this is a function. This function is a function of A. Now, writing this function, okay. Now let me write in a separate page, but you know, so writing this function, let me write here at the bottom here. So this function is theta n minus A transpose xn is a vector, okay? And then this is transpose multiplied by theta n minus A transpose xn. Okay? Then I take the expectation of that. Now, so I can write this way. Now when I write it this way, you know, what I get a quadratic form. So the quadratic form that I get, you know, so I get a quadratic form where, you know, I get the expectation, I get the expectation of theta n squared because it's this times that. Okay. Then I have the the mixed term. So I have A transpose xn and theta. Okay. So I have the expectation of theta n xn theta n. Then I have the same. I have A transpose xn and theta n, and then I have A transpose xn, A transpose xn. This one is transpose. Okay. So put it together. This means that this is equal to 2 times, and then I have the expectation of. Okay, so the expectation xn transpose theta n times A, and then I have a plus A x n transpose x n A transpose. Okay. Sorry, since it's a scalar, I can choose what to apply the transpose to. And so rather than applying transpose, it's better to apply the transpose to the second one. Okay. Then I need to compute the expectation. Here, I forgot to put the expectation. So let me call this guy here as P transpose. Let me call this guy here as R. Okay. So I get the equation which is represented on the top. Now it's a vector. Okay. So this one, what is P? Now looking at P is a cross correlation between xn and theta n.
X and theta are both vectors, right?
No, theta is not a vector.
Theta is not.
Theta is scalar and x is a vector. So this is a cross correlation between xn and theta n. Now xn includes all the coefficient of xn, of the vector x, which is used to estimate theta n. And this one is xn transpose. This is the cross correlation between xn and xn with itself. So this is the autocorrelation. Okay? So here I have the autocorrelation. And here I have the cross correlation between xn and theta n. Don't make a mistake, xn is a vector, theta n is a scalar. So writing in details, right here in details, this means that if my xn is denoting the fact that I have my vector and I'm focusing to the sample n, and I'm taking all these block of data, which is length capital N. Okay. And then by taking all these sample data, now, so that means that this is n minus 1, this is n minus 2, blah, 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 until I have n minus capital N. Okay? So that means that xn contains xn. You see, now is a bold, means it's a group of number. It's x n minus 1. X n minus 2, x n minus capital N. This is the vector I am considering. Okay? So that means that when I make A transpose xn, okay, this is equivalent to say it's a A0 xn plus a1 s n minus 1 plus blah blah blah. Okay? So that means that the output refers to the sample n. When I make the expectation of x n, let's transpose it, right? Okay, doesn't matter. And theta n, this is equal to the expectation, or we write the expectation to the individual term, is expectation of x n scalar theta n. Expectation of x n minus 1 theta n. And so on. Okay? So if I denote, that's another convenient, it's another convenient notation. So if I denote as a phi x theta as the cross correlation between x and theta, okay? Here I have phi x theta 0. Here I have a phi x theta 1, and so forth. That's why I say it's a cross correlation. Okay? Now, so my goal is to minimize that one. And that is a quadratic form. So you know everything about that. So you know how to calculate that minimization. Okay? So you can do it. So it's part of something that you can do. That's good. So that means that we know how to, for instance, to compute the minimum. So let's see on the other page. Okay. So I can calculate, the minimum for that. So that means that I can calculate the gradient of the function j that depends on a with respect to theta, with respect to a, I set to 0. Okay, and so what I get is this, the system of equation here, which is solving, which is finding what is the optimum set of coefficient. And now this set of coefficient is the filter, because A is a set of coefficient that denotes a filter. So by indicating this way, I can calculate the optimum filter coefficient. This is a set of equations called the Wiener-Hopf. Okay? So the optimum is by inverting R. And R is a matrix that contains the autocorrelation. Okay? So, simple. Okay? Now, another application. Is it clear? Okay? Now let's make another application. Now it's for our telecom colleague, okay? But that's useful also for the others, because you know how your mobile phone works, okay? You might be interested to know. At least someone has to show you one time in life, right? Okay. So what is, if you talk with the telecom, they say, oh, in my system there is an adaptive equalization. What is this adaptive equalization? Okay. Now let me show you. Imagine that you have look at this system. Okay. Now imagine that you have a wireless mobile system. Mobile means that you move. Okay. Otherwise it's called wireless. Okay, so it's mobile means that you move yourself. And by the way, there is all the infrastructure which is enabling you to move. Okay, otherwise you can't. So imagine that you have this moving system, and you have this transmitter, which is a tower, And this tower is transmitting to your mobile phone, but since you are moving with the vehicle, so you're running, okay? And I mean, the propagation setting is changing. Simply as simple as that. So since the propagation setting is changing, that means that the signal I expect is going to fluctuate. Intuitive, doing nothing, right? Now let's look at the zoom for that. Now the zoom of the experiment is the following. I mean, the wave field is not like in an ideal system where you have a very narrow waveform which is propagating from the transmitter to the receiver, because like in this case it's blocked by house, by trees, by whatever. Okay, so that means that the signal is propagating everywhere, and if there is a cluster, a group of houses, you reflect the signal from that. So the houses is helping you, is impairing you, or helping, okay? Because these houses is scattering the signals around. It's like when you are in the elevator. When you are close in the elevator, how can you use the mobile phone? Because you are almost in a Faraday shield, And the reason is that the signal goes into the edges, and the edges of the doors are acting as antennas, and those edges are backscattering into the elevator column, and then you talk by the phone into the elevator. Okay, I mean, making a very simplified description. So anyway, that means that even there it's reflecting to many places. So assuming that you transmit a waveform which is a phi of t, which is a rectangular, when you are at the receiver, one singular waveform is not represented by a rectangular, but just a superposition of a multiple part. And so you don't get a rectangular, you get this messy shape. And if the number of reflections are going to infinite, which is close to be the reality, you don't get this shape, but you get something which is close to that. It's getting similar to a Gaussian. There is a reason for that, forget about that. Okay? So then this is the waveform. So I transmit this, I get this. Okay? Now, your friends, colleague, know very well that when you transmit bits, you transmit one after the other. And the beauty of this story and the beauty of having a linear communication system is that once you understand what's happening in one bit, you make the linear superposition for all the others, and you can extend the property to all the other bits. So it's enough that we understand what's happening in one bit, and we calculate what? The impulse response of this filter. So this is the impulse response. So if this guy here is transmitting a set of samples AN, okay, on the other part of the receiver, I am collecting. Okay, I'm collecting this xn, which is by collecting the signal here, which is xn, and the sequence xn AN goes into this one, which is called the channel. It's a filter. Now, there are some technicalities how to get to this. So, you start with the nice picture, you get the distorted picture. Okay, that's the case, huh? And in the book there is my dog. So, the distorted picture is the picture of my dog. Okay, that one. So, for my wife, the wise man. My wife said that there's no picture of the dog in the book. Come on. Okay. So anyway, that's the system. Now this one is what the telecom people call it communication system. Okay. So the communication system is represented by a linear system, which is called channel, which is relating the bits in to the data that I sample out. Now there is some technicalities how to get that, you can read it. Huh? Now, what is important is the following. Since the car is moving, you know, due to the fact that the car is moving, the channel is staying there. Okay? And so, what you need to do, you need to track, to follow the variation of the channel. Now, you know, your goal is the following, technically. If I know HZ, I can put another filter here. Let me see how I call it, A probably. G. So I need to put another filter here, which is called GZ, which is called the equalizer. That previously we called the deconvolution. Okay. So we can put the G of Z, which has to be time varying as well. And that's why I get A, N, N. So we have a bits here. Actually, our telecom people say it's a symbol, but you know, never mind. We have a bits here, we have a signal here, and we have estimated bits. Okay, or signals. Okay, that's what is in your phone. Okay, in any phone. In any device that is moving, there is a system like that. So you need to make a G of Z variant. Now, remember, if you remember back to what we said, you know, in order to have this G of Z, I need to know this H. So if I know this H, I can put here G of Z, which is 1 over H. Okay, very simple. That is the simplest equalizer. Okay. And you know, so I can use this simple equalizer in order to compensate for the channel. We will see that it's not optimal, but you know, that's something that we will discuss. Now, for now, it's enough for me that it's clear this aspect. Now, in order to make a 1 over H, I need to know H. I cannot make a 1 over H as a filter, you know, as a Z transform of the G if I don't know H. So there is 2 stages. One stage where I estimate H, and the second stage is where I invert H. Okay? This inversion is called equalization. So the equalization is when I invert H. Now, so let's see how it's done analytically. Now it's done, okay. So all that you can read. What's happened now? Okay. So you know, you can read. I mean, for telecom, everything which is written here is like a bread and butter. You know, it's so obvious that you know this is another time. It's another time. Okay. Everything that is written here. Okay, so for the others, you know, you can give a look. I try to make it a very simplified model, but still realistic, for what is called a linear channel. Now, so let's look at there. So how can I make the adaptive, what is called adaptive equalization? Remember, we are on a mobile phone. Okay, now how fast is it moving? You know, it's moving very fast because I mean, if the wavelength of the wave field is in the order of like for 5G communication, so the next the future generation, okay, and in the future generation mobile device, the wavelength can be on the millimeter level. So if it is on millimeter level, that means that if I move just a little bit like that, okay, the channel changes completely. Okay. Now it's changing, but you know, in the future, it might be even more changing. And that's another reason why, there are 2 reasons why when you go on a train, you know, on a high-speed train, your wireless connection doesn't work, okay? One is that because of the channel is changing, and the other is due to another effect. If you are interested, you go to IEEE online, you go to IEEE, you have access You can read, we wrote a paper on why on the train, on high-speed train, your communication is degraded. I'm talking for telecom now. Is degraded, okay? And why it's better to go on the first carriage of the train rather than on the last. Okay, so remember, if you want to have a very good quality in mobile communication, on a high-speed train, go to the first or second carriage. Never go to the last. Okay? So, if you want to understand why, you read our paper. Okay? So anyway, it's now how does it work? Okay. Now the way it works is very simple. In telecom, we transmit a set of data that is called training, and a set of data that is called important data. Okay? Actually, you did something in the workshop because you were searching for the silent part of the music in order to estimate the filter, right? Now we do the same, except that we transmit a set in a block of data. Sometimes you call it packet, or you call it slot. Okay, so it depends on the context. If you're a network, you call it packet. If you are physical layer, you call it slot. It's the same story. So this interval, you have the first part of the interval where you transmit the signal that is known to the transmitter or receiver. This is called training. The second part, you transmit to the real data. So what you do is the following. In the first part of the data, you transmit a training which is known to the transmitter or receiver, and from here I estimate h hat z, which is I estimate the filter. Then on the data, what I do, I use this filter, apply gz by using 1 over hz hat, the one that I estimated, and then I equalize. So every mobile phone makes the following: receive the packet, estimate the channel, equalize. Receive the packet, estimate the channel, equalize. Estimate the channel, equalize. Estimate the channel, equalize. Okay? And the reason why you need to make so many in sequence is because the channel is changing. You need to make it, many times. But that's a non-stationary system. So wireless is non-stationary by definition. Now there are many other applications where you can look at the system as a non-stationary. I think last year I recommended to your colleague some examples. I don't remember, so perhaps I give a look at the rest next time. Okay. So anyway, so how is it? What is the model? Now the model is the following. I have a set of transmitted bits, if you like. This goes into the channel. There is a superimposed noise, and this is what I receive. Okay. So what I receive, what I need to do, I need to make a g of z. Now this g of z depends on the sector coefficient g now, which is similar to that, except that I call g rather than k. Okay. So this is my unknown. Okay, so that is my unknown. Now, how to get this one? Now I do the following. So in the first part of the training, okay, I estimate h, and in the second part I equalize, so which means I invert it. So what I can do is the following. I can do the following way. So in the first part of the system, what I need to do is at the output of this equalizer, I need to have these estimated data. So let me call this A hat. Okay? And now what I do is with this A hat, I compare this A hat with the reality. So now in the first part, since this one is known to the transmitter and to the receiver, so I have the file, the same training on the receiver side. So I compare the estimated one with the receiver, with the training sequence, And what I do, I try to iterate on that and minimize until this G is giving me exactly or close as close as possible as a training point. When I'm done on that, what I do is I take this switch and I open the switch. When I open the switch, that means that I'm not adapting. So what's happening is that all the data that flows here are using the estimated equalizer. And so I alternate in this way. Okay? Now, that means, when I manipulate my data, what I got a similar objective function, which is J, a new J. Now it depends on the new unknown, which is called G, but it doesn't depend. It doesn't matter what is the name of the variable. Tell me.
So, how are the G parameters initialized? Is totally random or?
Or you can, when you are the first,
Yeah.
okay, because when you are already running, you initialize with the previous stop.
Yeah.
Okay, so the first one you can initialize with one tap, one value different from 0. Okay, so it can be initialized random, it can be initialized with one coefficient different from 0. Okay, it doesn't change that much. As far as what is important is that the filter, okay, the filter that might be under a certain learning stage, so I need to learn the characteristic of the channel from the data. So this learning period should be long enough such that after the training I have very good, reasonably good, okay, the best I can, behavior of G. Okay, then once that I start the decoding. So I alternate learning or acquisition of the channel and decoding. Acquisition, decoding. Now this estimation of the transmitted symbol is called decoding. It's called decoding because I'm trying to understand what is the information. I'm decoding the information, extracting the information. But you can call, in our jargon, you can call estimation of the transmitted symbol. Okay? So, we can alternate them, estimating learning the equalizer, and then estimating the data. Learning the equalizer, estimating the data. Okay? So I'm simply changing the words, but saying the same concept.
So this kind of filtering with a loop, with a feedback loop.
Yeah, there is a feedback. You see.
We use it in this way because we have every time a training sequence and then we
Every time. Now, technically, there is a technical reason why the training sequence in practice is never put as a sketch, because it's more convenient to represent for you. But the training sequence is put in the middle, and the data or the transmitted data is on the edge, so on one side and the other. Okay. This is because in this way, under the variation of the filter response H, which is the channel, okay, this is minimizing the effect of the variation of the channel. But it's a technicality. That's a flavor for telecom. Okay. Now, so what is important is that we are back to the same formula. So we have again a quadratic formula to optimize, because we need to estimate G. Okay? So let's understand how to get these, how to optimize G. Okay? J. Okay? So at the end of, whatever is the algorithm, I come back to the point that I need to optimize this objective function. And this objective function is a quadratic form. Okay? So, now, rather than, if I need to do this in a real system, what I need to do is, I need to know perfectly the matrix R, which is the correlation matrix, and the cross-correlation vector P. Remember, P is the cross-correlation between x and theta. See there? Still there, right? Yeah. And R here contains the autocorrelation of the data, okay? Or the x signal. So, you know, I mean, in principle, I should know perfectly P and R. I should know perfectly the statistics, the correlation statistics of theta and x. Okay? Now that means that if I know that, so you know, I mean, basically the problem is solved because I mean I know perfectly everything. Okay. Now, in order to understand how to handle non-stationary signals, you need to first understand how to handle stationary signals. Okay. So you cannot understand how to handle a complicated problem if you cannot handle the simple one. Okay? So first of all, we need to know how to handle the simple problem, and then we will complicate. So let's make it a simple one. Now, you know, we know what is the optimal solution. I mean, I don't have the power capability in my system to calculate the optimal solution. So since I don't have the computational capability to calculate the optimal solution, basically I cannot calculate the inverse of R. Because the inverse of R costs to me n cubic. Okay? So you know, it costs me a number of operations which depends on the size of the matrix. And if I have a matrix and I need to compute the inverse, so if I have R and I need to compute R to the minus 1, this costs me, so if this one is n times n, okay, this costs me n cubic, approximately, okay? So if my matrix is, it's 5 samples, so the filter is very short, okay, so 5 to the power 3, is reasonable. But if my filter, like something that we are looking now for the 5G, for the 5th generation in millimeter wave, okay, so it's a project we are running. And the number of, the length of the filter is 100 samples, 150. So, if you need to compute 150 to the cubic, that means that you need to wait too long. Okay? So it's unfeasible. That's similar also for the voice. Okay? So sometimes, you cannot calculate this inverse. It takes too much time. Okay, so the difference, like when you press enter in MATLAB, you make enter, then you wait, poof, it comes up. Okay, it's not easy. It's not nice. Look at how the images are transmitted, are encoded. Okay, so sometimes when you are downloading one image and you are in a site, you are on a website, sometimes you get a very cluttered, very low frequency of the image, then you get a detail after a while. Okay, so this is because when you need to transmit a few data and that is a low frequency component of the image, then that costs a little bit. But then after a while it gets more and more focused. So the people get less embarrassed to wait hours, but the people like more to start seeing something, and then after a while you get a complete picture. Similar here. Okay? So that means that we can do the optimization of the mean square error, which is JA, by an iterative method. So the iterative method that I'm talking about is the so-called steepest descent, which means, what is a steepest descent? Now, what I want to do, I want to make an iterative procedure where, since I want to optimize a JA, I want to calculate this JA iteration by iteration such that when I get the A hat at the iteration K, when the number of iterations is going to infinite, this coincides with the true one. Okay? So I want to estimate a little bit, and then iteration by iteration, it gets more and more close to the true optimal solution. Now, how do I make it? You know, it's very simple. I calculate the gradient for that, okay? And then I make my step in the opposite direction with respect to the gradient. So what does it mean? You know, it's very simple. I mean, let me see if I have a picture. No, okay. I have my quadratic form, which I represent, you know, in contour line. That is a quadratic form, and this quadratic form depends on, let's say, A1, A2, and this is A1 optimum. That is A2 optimum. Okay. And by the way, this optimum coincides with the estimate. Okay. So that's what I want to get. Of course, I'm simplifying to dimension. Huh? Now, when I start arbitrary, as he was saying, you know, how do I initialize? Where do I start my procedure? So I start randomly. Let's say here. And my goal is iteration by iteration, go to the bottom. So what I do is this. When I'm here, I calculate the gradient. The gradient of a function, of a multidimensional function, is giving me the direction where this multidimensional function is going up. Okay, is maximally steep. And now, since I calculate the gradient with respect to all the dimensions, then, you know, when I compound the gradient, I have the sign direction in the space of where this function is maximally growing. So the gradient here is in this direction. So this is J, depends on the derivative of J with respect to A. Okay? J is the function, A is a vector, and this one is the notation representing the vector. Okay? So that is the direction. Now what I do, you know, if I want to move and I want to go to the minimum, then, you know, I move to the other direction. So to go there, you know, I simply take and minus the gradient with respect to A. Okay? Now, how long should I move? Well, I don't know. Then I just define a step size. And this is the step size. Okay? So what I do, you know, I calculate the gradient, I go to the opposite direction, and then I move. Then I calculate the gradient, go to the opposite direction, then I move. Calculate the gradient, going to the opposite direction, then I move. And then, you know, I reach the middle. Okay? So this is the essence of the steeper descent method. Now, we are very supported by the theory, which is saying that we are minimizing the quadratic form. And the quadratic is, you know, is a positive semi-definite, which means, you know, is a ball. So we need to go to the bottom of the ball. Good. So now the good news, by the way, is, sorry, I forgot to mention. There is this divided by 2, which is just a scalar coefficient, is only for convenience, okay? So the step size, if you like, you know, is all that, including these two. Now mu is not known. So mu is defining, how fast am I moving? Now think about it intuitively. If mu is a little bit, then, you know, I move with a small step, right? If mu is very small, I move with a little steps, and, you know, make, and then I go down. Okay. So this is with a small mu. If my mu is too big, then, you know, I move there, go there, then I go there, go there, you know, and this is for mu big. And that is for mu small. Yeah. Okay? So I cannot make a mu too small. I cannot make a mu too big. So how to choose the step size? Okay? That's our, you know, issue now. Now let's go to the analytics. Now the good news is that we can compute the gradient in the closed form. So the gradient which is computed there. Okay, so the gradient which goes there can be computed depending on the set of coefficient in the previous iteration. Now when I take this, plug into there, and then I have the update formula. Now look, the update formula never computes the inverse. So implicitly iterating with an infinite number of iterations, I'm computing the inverse, but I never explicitly compute the inverse. Okay, so here it is. This is the gradient, and that is the step size. So now that means that what I'm doing is the following. So imagine now, just to simplify, just to make a very, very simple reason. Imagine that I have a signal here. This signal goes into a filter, and the output of the filter, which is theta, is affected by noise. Okay? So that means that I know theta, I know x, I don't know the filter. Okay? Now, what I'm doing, I can do the following. I can take the signal here, take the estimated value of theta, calculate the error, and keep iterating until the error is, it's not zero, cannot be zero, can be as much as the noise. Look at that. When when this A is coincident with A0, that means that when I perfectly identify the filter, then the output here, this theta hat, is not theta, it's this one. Okay? So, at convergence, epsilon n with the theta A hat is coincident with Wn. Okay? Because the noise flows directly there, and there is not cancelled by n. Okay, from this block there. Now let's consider this, because it's a very simple model. Okay, we know x, we know theta, so we can easily calculate the filter. Okay. By the way, just to make it clear, this is called identification setting, because I'm estimating when I estimate f, my goal is to get AC, which is the unknown. Okay. Now let's see how to get a step size. Because right now, I'm talking blah blah blah, but what is a step size? How do I get a step size? Now, in order to understand all the analytics here, let me keep the analytics there and the sketch here. You remember some time ago that we made the diagonalization of a quadratic form. And then at that time we said, why am I doing this? Okay? Now is the time that you remember what we did at that time. So, I'm exactly repeating the same concept. Now, imagine that, you have a quadratic form. So the quadratic form is simply copying the energy of theta plus A transpose R A minus 2 times B transpose A. That is quadratic form in A. Okay? This is what we are minimizing. So I'm sketching here for 2 dimensions because I cannot make it with more. Okay? But what I'm doing in 2 dimensions is valid for any dimension. So this is A1 and this is A2. So this is first and second component of A. Of the vector A. And now this one is the optimum one. So it's A1 optimum that is A2 optimum. So ideally, you know, what I want, I want to get that. Okay? What we did in the past. Now, in order to diagonalize that, we did the following trick. We calculate, we translated the cycle coefficient with respect to the optimum one. So what we did, we calculate delta A. Yeah, delta A. Delta A, you know, is a cycle coefficient A minus the optimum. So we made the first translation. So we translate this delta A1, this is delta A2. So second part we did, we rotated the axis. And we call Z. Okay. This is Z1, and this is Z2. At that time, we said that the eigenvalue of a matrix R, that now we know is a autocorrelation, the autocorrelation vector, depends on this, the eigenvalue depends is reflected to the curvature of this quadratic form. Okay, that is something that we derive sometime. Now, so let's revisit the update. So what I'm doing now is I take this updating formula, okay? So the original update that I have is AK plus 1 is equal to AK plus mu, and then I have the gradient, which is P minus R AK. Okay? That's the update. Now, what I can do, I can remove from the left and from the right of this equation A optimum. Okay? Now, if I remove, so if I make a minus A optimum one side and minus A optimum on the other side. Okay? Now, if I remove, I don't change anything. But you know, I mean, conceptually there is a big difference because what I can do, I can just redefine the variable such that the optimization is referred to this new system of axes. And then, you know, I have the updated formula, okay, which is referred to the axis, where the axis, you know, is now indicated as delta A1, delta A2. Now, so now I take that one. Okay, so when I rewrite this, I rearrange all the terms at delta AK plus 1, which is equal to identity minus mu R delta AK. So, you know, what's happened is that I have a delta AK plus 1, which is a matrix multiplied by delta AK. Okay? Now, you know, I mean, I might stop here, but I may step forward. Now, I might stop here because I can calculate recursively, okay, the condition. Remember, we need to get a mu. So I can calculate the condition in order to guarantee the convergence. Okay? Remember, convergence is when delta AK infinite is going to 0. Okay? Because I mean, the convergence is when AK for K going to infinity is going to A optimum. So delta AK should converge to 0. Okay? Because the axes now are translated. Okay? So now, you know, when I look at this relationship, I can write that this one is identity minus mu R squared delta A minus 1. Because, you know, when I plug into delta AK the same formula, then I get this to the square. Now, this means that when I iterate many times, this is equal to identity matrix minus mu r to the power of k equal multiplied by delta A0. This is the initialization. When I start, as he was saying, how do I initialize, right? Okay. So what I want is, if I want that the system converge, I'm giving a different proof from here. Okay, I'm giving a slightly different proof from here, so that you know at the end you choose what you like. Okay. Now, so in order to guarantee the convergence, I need to say that for k going to infinite, this should go to 0. Now, so that means that all that, for k going to infinite, this should go to 0, regardless of the initial condition. Regardless of the initial condition. Okay? So, since I want the convergence, regardless of the initial condition for k going to infinite, that means that if I write in this, if I write here, let me write here. So what I got is this relationship. So I got that delta AK equal to I minus mu R delta A0. The convergence is guaranteed by the condition that this is going to 0 for k going to infinite. Because if this happens, this one is going to 0. That means that, you know, I'm converging to the solution. Okay? So, how to guarantee that? Now, I told you, I'm giving a different proof from there. How do I guarantee that? Now, to guarantee, okay, I take some room because I'm giving a different proof. Huh? So, now in order to guarantee that, you know, since I need to have a matrix such that its power is going to 0 for the power going to infinite, power going to infinite. Okay? So now I take the matrix R and I decompose by the eigenvalue. So if I take the matrix R and I decompose by the eigenvector eigenvalue, which I denoted U, so I have U lambda U transpose. Okay. Now, so you know, what's that? Now I rewrite only the argument. So I have identity minus U lambda U transpose. Okay. Then I have a mu here. Now, what is identity? You know, identity is, is U transpose. So then, you know, what I can do, I can write this one as U, then I have identity minus mu lambda U transpose. Now, let's multiply by itself. So, this is that, okay? I'm taking the curve. Now, let's take this one and multiply by itself. So, if I make a identity minus mu U lambda U transpose, multiply to the power 2, which is multiplied by itself, okay, that is equal to matrix U multiplied by identity minus mu lambda multiplied by U transpose time U identity minus mu lambda multiplied by U transpose. Okay. So now, this is identity. And so since this one is identity, this is equal to U identity minus mu lambda to the power of 2 u transpose. So if I generalize to that one, once I generalize to that one, what comes out is that, you know, if I take the power k, arbitrary k, of this matrix, which is identity minus ur, is the power of k of the kernel, of the inner part, the diagonal term, multiplied by u and u transpose. So this one is equal to, using this property, is equal to u, then I have identity minus mu lambda to the power k u transpose. Now we are almost finished, because, you know, I mean, what I want is that for k going to infinite, this one has to go to 0. This one has to go to 0. But, you know, u cannot be 0. So the only that can be 0 is this argument in the center. And this argument in the center is diagonal 1 minus mu diagonal of the eigenvalues. So if I take a 1 by 1 the eigenvalues, it comes out that the power k of that should be 0. And so I transfer the property. So I transfer this property to say that, you know, this matrix here is a matrix where I have 1 minus mu lambda 1. 1 minus mu lambda 2. To power k. So in order to have 0, I should have 1 minus mu lambda L to the power of k. So this limit for k going to infinite should be 0 for any L, which is any eigenvalue. That's the problem. So, you know, that means that, I mean, this argument should be smaller than 1. So it's enough that, you know, 1 minus mu lambda L, absolute value, is smaller than 1, because, you know, if this one is smaller than 1 to the power k, it's going to 0. Okay? So it's enough that I impose that this one is smaller than 1. So it comes out that, you know, mu is larger than 0, and smaller than 2 times divided by a certain number of lambda. Now, which one? So, you know, it's the worst case. Okay? It's the worst case that dominates. Okay? So, you know, then this is the condition of lambda and of the mu. Now I use a slightly different property. Okay, that's the same, you see. I use a slightly different property, except that I look at the z-axis. So z1 and z2 here, rather than looking at the property of the matrix. Now you can decide whatever you like in terms of the proof that we can choose. Okay, so we can look at the projection, which is z value, or you can look at the algebraic property of the matrix, you know, which is the one we choose. The results, you know, it's the same. And this is the condition. Okay, so you know, that's the condition that we get, which is, you know, that one is the same. That's the same thing. Okay. Now, you know, now, what is the benefit of this property? Now, you know, a couple of minutes and then done. What is the benefit of this property, this behavior? Now, the benefit of this behavior is that, you know, we can establish the convergence property on every direction. So what does it mean? It means the following. You know, if I start from here, okay, and I make a set of steps. Okay, these are the steps that I make. Let me make it a thick one. Okay. So I start from here, and then, you know, iteration by iteration I go there. Now, what we notice there? We notice that, you know, if I look at the two axes, what's happening in Z1, what's happening in Z1, in Z2, okay, Z1 and Z2, huh? You know, what we notice that, I mean, our problem is totally decoupled in the optimization steps. So, what's happening in one direction is decoupled from what's happening in the other direction. It's because we choose the specific axis. Okay, and the axes are the principal axis of the quadratic form. So, essentially, you know, since the eigenvalues in this direction are higher, okay, it's steeper. Huh? So, in this direction, you know, the convergence is faster. So, essentially, it looks like if I'm converging there, and then it's converging slowly on the other side. So, I'm faster converging in this direction, and slowly on the other. Now, what is the, you know, the convergence time? Now, the time constant is indicated there. So the lambda is ruling the convergence time. Okay, so how many iteration takes? Remember, this time is not second; it's measured in iteration. Okay, so this one is approximately the number of iterations for the convergence along the L direction. L means eigenvalue 1, eigenvalue 2. Okay. So then, you know, this depends on mu as well. So the number of iterations to get the convergence here depends on mu. So it's 1 over mu lambda. Now if I choose mu, that means that if mu is small, okay, so that 1 over that mu makes the time of convergence much longer. Okay? I cannot choose, you know, any value because, I mean, I'm constrained to have a mu that is equal to that. Okay, so since the convergence, now, you know, you can imagine that it's like I need to have a convergence on one principal axis, I need to have a convergence on the other principal axis. So imagine that in my dimension the problem is n, 100. I have a 100 coefficient with filter, and you know, in order to guarantee to declare the convergence of the filter, every dimension has to be reaching the convergence. And so, you know, what is ruling the convergence is the maximum time. So it's like to be a group of people. So we start all together, okay? And so, you know, and we need to go to the bottom of the valley. But I mean, there is one that is very slow. And so in order to declare that the group has reached the convergence, this convergence time depends on the slowest one. And so essentially what I say is that the time for convergence, okay, is equal to the maximum of the time for all. Now, since the maximum is the maximum of 1 over lambda, so that depends on the minimum eigenvalue. Now, the step size depends on the maximum eigenvalue, and the time for convergence depends on the minimum eigenvalue. So if I put all together, I can notice that the time for convergence is larger or equal than 1/2. Okay, it doesn't matter 1/2. So the ratio between lambda max and lambda mean. Now the lambda max is the lambda max of the matrix R, and the lambda mean is the lambda mean of the matrix R. So the convergence of the algorithm depends on the ratio between the largest eigenvalue and the smallest eigenvalue. Okay? So you know that's important. Okay? Now we will talk on that later. And so, you know, I gave you also an intuitive view of the convergence. You can look, you can read it, okay? Because, you know, I made it. So essentially, you know, since I'm separating a multidimensional problem in a set of one-dimensional problem, you know, essentially my step size should be done such that when I start from one point here, I cannot make the step size so big that, you know, when I make a steps, I go higher than before. So for the convergence, you know, when I start from one point, I need to make a step size. The step size means how long I make, okay? So the step size should not be made such that I go higher than before. So when I start from here, I need to go lower than before, not higher. Okay? So now, you know, looking at this behavior, this means that when I start from here, I need to go lower. No, so that means, you know, I pump, perhaps I make a bouncing here, but it has to be lower. Okay, so that's another look at the problem of defining, the convergence of iterative algorithms. Now, remember, so far we have not discussed about adaptive. We are simply studying the problem of making the estimation of the optimum filter to be iterative, which means iterate by one. And next week we will make adaptive, okay? And that's it. We will discuss it.